Pancholi, Assistant Professor in the LJ Institute of Engineering and Technology in Department of Electronics and Communication. This video is about subject Digital Image and Video Processing. So friends, in this video, we are going to discuss regarding the wavelet. So in the last video, you learned about the wavelet. What is the wavelet that we learned? Now, in today's video, we are going to learn about the continuous wavelet transforms and the image pyramids. So wavelet based the multi-resolution analysis and the wavelet properties, image pyramids. So these are the topics for this video. So very first, the uncertainty principle. So as we know that the uncertainty principles which states that a function cannot be simultaneously concentrated in both the physical space and the Fourier space. So the uncertainty about the Fourier transform which we discussed in the last video. As we know that the Fourier transform gives the data that is in the frequency domain and the wavelet that gives the representation in both the time and the frequency domain. So now we are going to study about the wavelet. So the solution to get the better information in the both the time and the frequency domain, that is the use of the wavelet. So function sin x, that is a wavelet if it satisfies the following condition, which is minus infinity to infinity sin x dx equal to 0. It is minus infinity to infinity sin square omega whole square upon the omega, okay, d omega, it is equal to c omega less than infinity. C omega, that is the wavelet. So what is the purpose of the continuous wavelet transform? So the continuous wavelet transform that is used to decompose a signal into a wavelet. Now wavelet, they are the small oscillations that are highly localized in the time. As we have seen in the previous video that whenever the Fourier transform you will convert into the wavelet transform using the wavelet transform, so we will have the small wavelet. But now we need a continuous wavelet transform which gives the small oscillations, okay, and which is localized into the time. So this way the wavelet transform, okay, this is what the continuous wavelet. So now this continuous wavelet that gives the information both in the time as well as the frequency domain. So the continuous wavelet transform of a function fx, which is introduced by the Wavelet and which is defined by the following equation. So it is w into f of ab equal to minus infinity to infinity fx sin abx dx. So as we know that the windowed function or the spectrogram which we get from the Gabor function. So what is that? The Fourier transform which will be multiplied with the windowed function defined by the Gabor, which gives the information that is both in the terms of the frequency as well as the time. So the inverse transform of it, that is denoted by the fx is equal to 1 upon c sin minus infinity to infinity, again minus infinity to infinity, 1 upon alpha raised to 3 by 2 w f of ab sin abx dA dB. So now here we get the inverse wavelet transform, okay, of the continuous function. So this way the c sin that is defined in the wavelet and which in the continuous wavelet transform record whatever the changes in the fx that will be stored in terms of the c sin, and which can be very useful in the compression or the noise removal, since changes at the finer scales can be omitted in the reconstruction. So what is the need of the multi-resolution image analysis? Now as we know that in the wavelet transform we are taking the different scales, okay, for the different component, and we can get the image that is having the very high resolution. So our common observation, that is what? That is that the level of the details within the image, which varies from the location of the location to location. As we know that the some locations that contains the significant details where we require the finer details, okay, so for the analysis, and there are some other locations where the coarser resolution representation that is required. So wherever the requirement and according to the particular requirement, we can apply the scaling to the particular value. Mean if the significant details are available from the image, and again if we are adding the scaling component, okay, then that may not give the particular information. So the multi-resolution technique, that is what? The multiple scaling that can be applied to the different value available in the image, and that way we can get the image that is having the good resolution. So that is why the multi-resolution representation of an image, which gives a complete data or complete idea about the extent of the details existing at the different location, from which we can choose our requirement of the desired detail. Mean that the complete data we have. Now the point we need to identify that wherever the pixel value that is not up to the mark, which is not able to give us the finer detail, so at that point the scaling that must be required. But the point at which the scaling that's not required, the lower level value, okay, that can be choose for getting the high resolution images. Now the multiple resolution represent the efficient compression by exploiting the redundancies across the resolution. So it can also remove the redundancies, and that way we can have the better compression. So that is why it can use for the compression as well as the DSP processing. So wavelet transform, that is one of the popular but not only the approach for the multi-resolution image analysis, and it can be also used for the subband coding. Okay, so in the subband coding this can be also used. Okay, so it is that can be why it is used in the subband coding. Now the scaling function and the functional subspace. What is the scaling function? So any function that is the fx, mean this function that is your image, so that can be analyzed as a linear combination of the real valued expansion function phi k x. So it is f of x equal to sigma k phi k x into alpha k. So here we are adding, we are multiplying the some factor, so by which the image that can be expanded. So now that is the function that is for the expansion, where k is an integer index of the summation, and the alpha ks are the real valued expansion coefficient, and which form the expansion set. So now this expansion function we can write, that is phi r s x. So 1r, okay, that is what the expansion factor, and s that is for the image space. So it is 2 raised to r by 2, that's my expansion factor, and the phi 2 raised to r x minus x. So it will be provided some the delay or the decay, okay, while the expansion that has been done. So let us compose a set of the expansion function, that is the phi r s of x through the integer translation and the binary scaling of the real square integrable function phi x. So now it is phi r s x equal to 2 raised to rs, okay, and it is phi 2 raised to r x minus x. So this is the function. Now there are the various properties. That are the two main property of the wavelet. that are the admissibility and the another one that is the regularity. So regularity, that is the another property. So now what is this property admissibility? This admissibility which states that the minus infinity to infinity sine of omega whole square upon the modulus of omega d omega, that is a less than infinity, where the sine t is a wave in the time domain and the sine omega, that is the Fourier transform of the sine t signal. So now in practice the sine omega will always have the sufficient decay, and therefore the admissibility criteria reduces to the requirement sine of 0 is equal to 0. So it is minus infinity to infinity sine t of dt equal to sine 0 is equal to 0. So each wavelet transform must meet the requirement that it should be integrated to 0. Okay, so that is why the transform wave above and below the x-axis and the average value of the wavelet in the time domain, that must be 0. So in addition, the transform is well localized in the time domain. So that is why the wavelet which can be defined over the time, which is the 0 less than or equal to t less than or equal to n. Okay. So the provides the set of the basic function sine t in a continuous time, and sine jkt is a set of the linearly independent functions, and which can be used to produce all the admissible function ft. So expression is the ft is equal to sine jk bjk sine jk of t, where the sine jk, that is 2 raised to j. Now again it was the r by 2, that was for the expansion. For the compression, this function means the compression function, that is 2 raised to j t minus k, indicates a wavelet that has been compressed j times and shifted k times, and bjk, that is what it is known as the constant. Fine. Next is the regularity. Now this regularity is what? So regularity means to ensure the wavelet transform decreases quickly with decreasing the scale. Now as we know that while the scale that is reduces, okay, the wavelet transform that decreases its value. So the condition which is that the wavelet function should have some smoothness and concentration in both time and the frequency domain. So that is why the taken together admissibility and the regularity, that components have in the wavelet, okay, and which provides the decay. So now this is about the wavelet, okay, and this wavelet the efficiencies, okay, which properties that can be used in the wavelet transform. So thank you very much everyone. Keep watching LJIET Electronics and Communication for more updates on the electronics and communication videos. Thank you very much everyone.